Look out your window right now at the skyline. You've got towering skyscrapers, massive bridges, endless highways. It is almost impossible to believe that every single one of those massive, heavyweight structures rests entirely on the performance of a simple, fine gray powder. Well, you're in exactly the right place today as we decode the true DNA of concrete. We're going to completely unpack the 6 critical physical properties of cement. Let's dive right in and uncover the microscopic battles and the really rigorous lab tests that literally keep our modern world standing.
Welcome to the lab. Because before a single drop of water ever hits a mixer on a job site, engineers and concrete technologists rely on 6 uncompromising tests. We're talking fineness, standard consistency, setting time, soundness, compressive strength, and splitting tensile strength. Let's get right into the very first one.
Property number 1, fineness.
We are starting small here, like literally microscopic. Fineness is all about the particle size distribution of the cement powder itself. Think about dropping sugar into your morning coffee. A solid sugar cube takes kind of a while to dissolve, right? But if you pour in fine powdered sugar, it dissolves almost instantly. Well, cement works the exact same way. Finer cement particles give you a massive surface area, and that means much faster chemical reactions with water, a process we call hydration. Faster hydration leads directly to a much quicker development of early strength in the concrete.
So how do we actually measure this in the lab? We basically have 2 ways. The first is a straightforward sieve test using a 90-micron IS sieve, number 9. We shake 100 grams of cement for 15 minutes, and for ordinary cement, the residue left sitting on top shouldn't exceed 10%. But the modern, highly accurate way to do it is with the Blaine air permeability test. This machine actually forces air through a prepared bed of cement to figure out the specific surface area. That's the total surface area of all the particles in just 1 single gram of cement, usually measured in square centimeters per gram. The rule of thumb? The finer the grind, the harder it is for that air to push through.
Moving right along to property number 2, standard consistency.
Now we're moving from a dry powder to a paste, and we are looking for that perfect Goldilocks zone of water. We absolutely can't have a paste that's too dry, and we definitely can't have a soup that's too wet. We need an exact baseline, which we call percentage P. To find P, we use what's called the VCAT apparatus. We take 500 grams of cement, mix it with a trial amount of water, let's say 24%, and fill the mold. Then we release a standard 10mm diameter plunger. We want that plunger to sink into the paste under its own weight and stop exactly 33 to 35 millimeters from the top. If it doesn't, we clean the whole thing up, adjust our water percentage, and try again until we hit that exact penetration depth. Oh, and to ensure perfect scientific accuracy, this entire test has to happen at a constant 27 degrees Celsius and exactly 90% humidity.
Which brings us to property number 3, setting time. Once we know our standard consistency, we can actually unlock the timeline of construction. The exact second water touches that cement, an invisible chemical clock starts ticking. At 0 minutes, water is in. From that moment, the concrete has to remain plastic and workable so the crews can actually mix it, transport it, pour it, and finish it. This workable window ends at the initial setting time, which for ordinary Portland cement has to be a minimum of 30 minutes. If it sets faster than that, you've got a complete disaster on site with concrete hardening right inside the mixer. But eventually, obviously, we do want it to harden, so we look at the final setting time. That's the point where the paste completely loses its plasticity and turns into a hard mass that can actually bear loads. This has to happen within a maximum of 10 hours, fast enough to protect it from the weather, but slow enough to let the crews do their jobs.
Next up, property number 4, soundness.
Okay, so let's say the concrete has set and hardened perfectly. We're safe, right? Well, not necessarily. And that brings us to long-term chemical stability. Soundness is a cement's ability to retain its volume after hardening without any delayed expansion. Think of baking a loaf of bread. If the dough expands in the oven, that's great. But if your concrete starts expanding after it's already turned to solid stone, that is absolutely catastrophic. This delayed expansion is caused by unreacted free lime or excess magnesia that got trapped inside the cement during manufacturing. Over time, those compounds react with moisture, they expand, and they create massive internal stresses that will literally rip the hardened concrete apart from the inside out.
To make sure that doesn't happen in the real world, we basically have to accelerate time in the lab using 2 specific tests. First up is the Le Chatelier test. We put cement paste inside a tiny brass cylinder with 2 long indicator arms. Then, we actually boil it in water to accelerate the reaction of the free lime.
Those arms will spread apart as the cement expands, and the rules are strict. This expansion cannot exceed 10 millimeters. But the Le Chatelier test only picks up free lime. If a batch of cement has more than 3% magnesia, we have to bring out the heavy artillery, the autoclave test. Here, we blast a hardened cement specimen with high-pressure steam at 21 kilograms per square centimeter for 3 whole hours. If it survives that autoclave without expanding past its limits, we know for sure our building is going to be fundamentally sound for decades to come.
Moving on to property number 5, compressive strength.
So, the cement is fine, the water is perfectly proportioned, it sets right on time, and it's chemically sound. Now, it is time for the ultimate physical showdown. How do we know how much weight our concrete can actually hold up? Well, first we take these 150 millimeter steel cube molds. We fill them with concrete in 3 distinct layers, and we tamp each layer exactly 25 times to force out any trapped air voids. Then comes the waiting game. We cure these cubes in a 90% humidity room at 27 degrees Celsius, usually for a full 28 days. Once they're fully cured, we place the cube into a massive compression testing machine, a CTM, and we don't just abruptly smash it. We apply continuous, steady load at a rate of 140 kilograms per square centimeter every single minute until the concrete finally gives up and shatters.
The math behind this highly destructive test is actually elegant and incredibly simple. Compressive strength, which we denote as FC, equals the maximum failure load, P, generated by our testing machine, divided by the cross-sectional area of our cube, A. That gives us our characteristic strength, usually measured in newtons per square millimeter, which you'll also hear called megapascals. This single critical number is what dictates the structural capacity of columns, walls, and foundations all over the globe.
Finally, we hit property number 6, splitting tensile strength. Look, we all know concrete has an Achilles heel. It absolutely loves to be squeezed, but it hates being stretched or pulled apart. To measure this specific weakness, we change our shape. Instead of a cube, we cast a standard concrete cylinder, 150 millimeters in diameter by 300 millimeters long. But here's the trick. We don't stand the cylinder up. We actually lay it down horizontally on its side right in the testing machine. Then, we apply a compressive load straight down along its length. This top-down squeezing actually forces a horizontal pulling force, a tensile stress, right through the dead center of the cylinder. We keep ramping up the load until the bottom fibers crack and the entire cylinder literally splits perfectly in half, straight down the middle. This test tells structural engineers exactly when the concrete will crack under bending forces, which is absolutely crucial for designing things like suspended beams and floors.
And there we have it. Let's step back and look at the complete picture for a second. The entire journey from a microscopic gray powder to a towering, indestructible stone is governed completely by these 6 pillars. The rapid hydration unlocked by fineness, the perfect paste born from standard consistency, the crucial construction window defined by setting time, the lifelong stability ensured by soundness, the ultimate load-bearing power proven by compressive strength, and the critical resistance to cracking mapped out by splitting tensile strength. These aren't just arbitrary lab tests, guys. They are the uncompromising laws of physics that dictate the survival of our modern infrastructure.
So, the next time you're walking across a concrete pavement or gazing up at a massive high-rise, I really want you to remember the microscopic battles, the high-pressure steam, and the massive crushing machines that proved that material was safe long before it was ever even poured. How will you apply this deep understanding of these 6 properties to your own studies, your lab work, or your next major structural design? Let that question sit with you for a bit. Keep learning, keep building, and I'll catch you in the next explainer.